Okay, so plan for today's session is we will devote 15 minutes just like we did in the last week first class for this, so that there is a comparative study which happened in the starting of the course, and this is towards the end. You have more idea, you all have more idea is around this thing, and the plan is ki tomorrow we will evaluate, but we will discuss basically an analysis, not in one to one or individually discuss, but an overall analysis key what was the growth in that. So the first 15 minutes is allocated to this, and post that we will move on to peer learning. And for peer learning we have planned model 2, 3 and 4, model 2 being Fourier domain, and model 3 being sampling, and model 4 being Laplace and Zepf transform. Same rules, 30 minutes would be dedicated to each, so that each can be covered properly. If needed more time, then it's okay.
Model 2 is 4 years, model 3 is
Sampling. Model 4 is Laplace. But yeah, abhi to ye hai.
Laplace and Z.
Yeah. So let's get it done. Let's say the deadline we put is for 11:40 am.
They encourage you to improve your the things that you submitted earlier. So don't try and not copy the things that you wrote already. Try and do improvement. The improvement should be in line with whatever you learned in this. No, this is 3 points here, right?
Yep. The same way which we did in the last week. ये अलग है. This is for the later half of the session. अब ये है. We will start with the today's session, and this is done. So before the peer learning, we will focus mainly towards model 2 and 3 signal analysis and Fourier domain and sampling theorem. But before that, Suketu has posted some questions and he would like to discuss some. Suketu.
Yeah, so just one question that I wanted to discuss, and it has lots of subparts. And yeah, so we have 5 important properties of systems that we discussed in module 1. Just quickly recollect them. Causality. Linearity is a combination of 2 things. What are those? Stability in the Bibo sense. Shift invariance or time invariance, whatever. So you would expect that all of these are independent, right? And by independent I mean that if a system has one of these, you cannot directly say that it has the other. So naturally you would want examples ki, you know, is there a system which is additive but not homogeneous, but stable but not shift invariant, but causal, and so on. So in such a way you should be able to construct examples of 32 such systems, right, because you could have yes or no to each of these 5 properties. And so that is the assignment that was given in the group. Yeah, so for example, let's start with a system that has none of these. Okay, so any examples? A system which is not causal, not additive, not homogeneous, unstable, and shift variant. Any guesses? Anyone has examples? Sorry, why? AT. No, but it should be, so I have a signal x of t and to it I am associating some signal y of t, right? So what is y of t in terms of x of t? X of t plus ax of t plus m. Oh, outside. Okay. Which property, does it satisfy none of these properties? It satisfies causality, right? What is causality? If you can determine the value of y of t if you have access to the current value of x of t and all values of x of t before that. That is called causality. So this is causal. So this is not an example. Now suppose I replace it with x of t plus 1. Does it satisfy none of these properties? Definitely it's not additive, it's not homogeneous. Is it stable? It is stable. Why? Because if I have an input x of t which is bounded, then y will also be bounded, right? Because y will be which is a finite real number, right? So it is stable. So now you need to convert this into something which is unstable. So how do you do that? So a simple thing to do is, okay, you could have a constant, or what you could do is you could multiply it with the, does it satisfy any of these properties? For simplicity, I'll remove this a also. Y of t is t e to the power of x of t plus 1. Is it causal? Is it additive? Homogeneous? Stable? Why is it not stable? Correct. So if I just give x of t equal to 1, then itself you have an unbounded output, because y of t is equal to t, which is unbounded, right? So it's not stable. Is it shift invariant? So how do you check for shift invariance? So if I have this system, I will give x of t minus t0 and I should get y of t minus t0. But are we getting that? We are not getting that. Why? Because of this factor of time. Right. So this is our first example which satisfies none of these things. Okay. Causality, additivity, homogeneity, unstable and shift variant. Now suppose I want just shift invariance and I want none of the others. Can you construct such an example? Think about it, maybe 2-3 minutes. See if you can come up with such an example.
Causal, additive, homogeneous.
It should not be any of those. It should be just shift invariant. It should be non-causal, non-additive. Yes. This. It's stable, right? So definitely it's not easy to find out.
First we take a system which has all these properties.
Okay, so let's take that.
And then we move one by one.
Okay.
We will get easily.
Sure. What do you start with? So there's no easy way to sort of determine. So for causality, if you want to avoid, you just whatever x of t you have, you just replace it with x of t plus 1 or x of t plus 2. That much you can do, right? Unstability you want. So if I have some bounded input, right, and I want to make the output unbounded, what are some ways to do that? So for instance, if I put x of t in the denominator and if x of t is approaching 0 somewhere, then my output will grow unboundedly, right? So let me try this. Just I am trying. Is it causal? It's not causal because it depends on t plus 1. Is it additive? Clearly it's not additive because x of t is in the denominator. It would be homogeneous if this value was 0. But now because this is non-zero, if I scale x of t with some constant and I scale y of t with some constant, then this constant is also going to change. So I won't get y of t minus t0. So it's not homogeneous. Is it stable? It's not stable. Why? Because if x of t approaches 0, x of t plus 1 approaches 0, you see that y of t grows unboundedly. So it's unstable, and you can check that it's shift invariant because there's no factor of time involved, right? So this is an example which is just shift invariant and it has none of the other 4 things, right? So that way you should be able to construct 32 such examples. Now we don't have much time, so what I'll do is I'll just take one example of each. So let's do the easy ones first. This we've done. Now give me a system which is only causal and has none of the others. This is very easy to do. Just right, I just remove the non-causal. Yes? Yeah. No, so if x of t plus 1 tends to 0, then y of t grows unboundedly, right? I'm not talking about the value. See if, correct, but it will grow unboundedly now. See, if this is my x of t, near this, y of t will grow unboundedly, no? What does unbounded mean? Means that for any real number, if I have some signal x of t and I say unbounded, for any real number r, correct.
So if it's tending to 0, it will always, we will consider it 1, na?
I mean, if it's tending to 0, it will tend towards nothing. Minus infinity and plus infinity are not real numbers. See, I'll tell you the definition. Correct. Exactly. So let me tell you. See, what is the definition of an unbounded signal? If I say x of t is unbounded, that means for any real number r, I can find a time t such that x of t is bigger than r. Can I do it with this? So I can always go close enough to the point where x of t plus 1 is 0, which will make y of t as big as I want, right? So in that sense it is unbounded. Unboundedness never considers values at points. So in some sense it's like saying, you know, y of x is equal to 1 over x, where x is not 0 and 1 otherwise. Is this a bounded function? It's not bounded, right? Because you can achieve arbitrarily high values using y if you get close enough to 0. That is what stability or instability means. So 3 cases we've done: causality, shift invariance, and none of them, right? So can you give me a system which is only additive and none of the others?
What is the third thing you did?
Yeah, so I have constructed 3 systems I have constructed so far. One in which none of these 5 hold, right? That was tx to the e to the power of x of t plus 1. If I want just causality to hold, I will remove the non-causal part of this and none of the others will hold. If I want just shift invariance, then this is an example, right? So this is done, this is done. Now give me an example which is only additive and none of the other 4. Non-causal, non-homogeneous, unstable, shift variant and yet additive. So typically if you want additivity but not homogeneity, the typical thing to do is you just consider conjugates. So consider this system, y of t is equal to complex conjugate of x of t. Is it additive? Is it additive or not? It is additive, right? Because for complex numbers a and b, a bar plus b bar is a plus b bar. A bar denotes the complex conjugate, right? So this is additive, but is it homogeneous? So if I put cx of t, I will actually get c bar x bar of t. So this constant is different. So this is not homogeneous. So this is the typical way to construct systems which are additive but they are not homogeneous. So keeping this in mind, can you construct an example? I want only additivity and none of the other 4.
That's an example, right?
No, it's causal, no? It's stable also. I want just additivity. I don't want causality, homogeneity, stability or shift invariance. I want none of those, just additivity. Integration. Integration, the problem is I want my system to be operable on all signals. So in general, a system S, so if you consider the set of all functions from real numbers to complex numbers, I want my system to be a function from this set to itself. And if you assume, if you put integration and all, then you assume that your signal is integrable, which need not be the case, right? I mean, there are non-integrable signals also. Correct, correct. Yes, but I want the system to be applicable on all signals. There are some signals for which your system will not be applicable, no? The signal integral does not exist, how will you pass it through that system? That is why I don't go for differentiation also, because that assumes that the signal is differentiable. Yeah, so any ideas using this construct? Okay, correct. Right, so what is the system you are suggesting? Huh? Right, but what is the correct, correct, but are you sure it is not stable, it is not homogeneous, it is not causal and all that? Have you checked? Because I don't want any of those. Right, so using this construct, I'll give you that example. Again, don't blame yourself if you can't come up with these, because they are genuinely, you typically think additivity and homogeneity are not independent. That is what intuition tells you. It's not easy to think of this, but actually they are independent. So the system we'll see is it additive? Is it additive? It is additive, right? Is it causal? No, because it depends on t plus 1. Is it stable? It's not stable, because if time is very small, you can make it unbounded, right? So it's not stable. Is it homogeneous? Again, because of this one, it's not homogeneous. And is it shift invariant? Because there's a factor of time, it's not shift invariant, right? This is a system in which only additivity is there and none of the others are there. Okay? I'll just give one more example and I'll leave the fifth one to yourself. Construct a system which is only stable and none of the others. Try this. This should not be too difficult. So I want only stability, I don't want shift invariance, I don't want homogeneity, don't want additivity and don't want causality. So in general, if you consider sort of exponential systems, so suppose I take y of t equal to e power x of t. This will easily give you access to systems which are not additive and they are not homogeneous, okay, and this is stable. So now you just need to make it non-causal and shift variant. So to this system you have to make some changes so that it becomes non-causal and it becomes shift invariant, right? So can you do that? Yes, yes, yes. X of 2t plus 1, e x of 2t plus 1. Is it shift invariant? It's not shift invariant, right? T plus 1 or 2t plus 1? I want shift variant. This is shift variant, right? Is it stable? It's stable because if x of t is bounded, then x of 2t plus 1 is also bounded, y of t is also bounded. Is it additive? It's not additive. Homogeneous? It's not. Causal? It's not. Shift invariant? It's not. So this is a good example, which is only stable. It's not any of the others, okay? Correct. And now we'll go the last example. So what is left? Only homogeneous, correct. So give me a system which is only homogeneous and none of the others. So if you want homogeneity and you don't want that, Sorry?
d by dt of x of t.
Correct, that is what I said. It's a good example, but I don't want to give that because it assumes your signal is differentiable. I don't want to do that. Now I want to consider any function from real numbers to complex numbers, and I want the system to be applicable on that. So if I take something like x of t equal to, I don't know, the unit step for instance, and you say your system is y of t, the derivative of x of t, then it doesn't really make sense, right? So typically if you want x of 2t plus 1, is this stable? I don't want stability, I just want homogeneity, I want none of the others. Essay, still stable, no? See, if you give a bounded input, it should be a bounded output, so that's why it's stable. So if you want, yes, sine of x of t, is it stable? Extremely stable, so no. 1 over x of 2t plus 1. Is it causal? Is it additive? Is it, no, but this is not a system first of all. What happens if x of 2t plus 1 is 0? You have to define that. What is the value if x of 2t plus 1 is 0? You have to give some value, no? 0. Is it causal? No, it's not. Is it additive? No. Is it homogeneous? Yes, because 0 is kept here. If there was anything other than 0, it would not have been homogeneous. So it's homogeneous. Is it stable? It's not stable. And is it shift invariant? No, because there's a factor of 2t here, right? Correct. This is a good example. And in such a way, this is just 6 of the examples that we've considered. Actually, there are 32. So, this is a very interesting problem that you can give to your students, You find all such systems and you convince yourself that actually all these properties are independent, right? So, yeah, that is all I wanted to discuss.
Okay, so today we will talk about second module, that is transformation from time domain to frequency domain. All of are aware of this Fourier series, yeah. We have done a lot of maths. Yeah, so those maths things I will not cover, how to solve. All of us know that how to do the integration, and we can calculate a n, a naught, b n. Okay, so here just we will talk about what is the significance of a naught, a n and b n, and why really we are calculating. And when we are calculating a naught, a n and b n, and we are saying that we have converted our signal from time to frequency domain. Okay, what does mean by that? So those kind of meaning we will discuss. Okay, we will not go to detail of how to solve that one. Solving to all of us did that, yeah. Since 12th standard we are solving this kind of problem, yeah. It is just the integration only. Okay. So before going for Fourier series, first of all, just there are a lot of signal property, yeah. Sir has also covered periodic or non-periodic. Okay, so we know that what is that. So those two properties are required, yeah. And second property is required is even and odd signal. Okay, we can divide any signal into even and odd component, or we can categorize signal as a even signal and odd signal. Why it is required? Once we go into Fourier series, when we discuss a n and b n, at that time this concept will come handy. Okay. So let us see what is even signal. Okay, what is even signal? Yeah, what is even signal? Yeah, even if I time reverse the signal, I will get the same signal. Fine. Fine. X minus t is just a time reversal. I am just flipping my signal along y axis. Okay. If you flip this signal, this same part, you can see that this part will come over here, this part will go over here. So we will get the same signal. Any doubt in even signal? So whenever we get a signal, if we flip, if we are getting same signal, that is our even signal. Second signal is odd signal. Okay. So let us flip this signal into time. What will happen? Okay, so this part will go here and this part will come here. Okay, are they same? No. So if I flip that signal along x-axis, what will happen then? So suppose let us take x of minus t. Fine. So what will happen? So this signal is there. Now this signal will go here. This signal will go here. So this signal is with us. Okay. This signal is x of minus t. So both signal are same. These two signal are same. No. So let us do one more operation. Let us multiply this signal with minus 1. Now what will happen? This will come down here. Am I right? This will go up here. If we connect them, so we got the same signal. Okay, if signal follows this property, then we call this signal as a odd signal. Fine. So we know that what is odd signal and what is even signal. Okay. So can you tell me that this signal is even signal or odd signal? Even signal. This signal is odd signal. This signal is, look here, some of you are saying that this is even because like triangular shape we are like focusing on. Okay, shape is fine, but we have to see that where this signal is originating. This signal is originating at 0 and going up to 1. If I flip that signal, then it will go to minus 1, origin will remain at origin. So we will not get the same signal. Even if we flip that, so we will get something here. Yeah, even if I flip that signal, I will get something here. Yeah, so this is neither even nor odd. Fine. But those kind of signal, what we claim is that any signal, if it is neither even or odd, then we can have even component as well as odd component of this signal. Fine. I can get even part of this signal, I can get odd part of this signal. Fine. So one more question I would like to pose. Okay, what is the DC component of this signal? Is there any DC component in this signal? What is DC component? If we take the average area of any signal, if it is non-zero, then we call it DC. So this area we can calculate here. Is it non-zero? Non-zero. So it has a DC component. What about this signal? Yeah, this height is minus 1, this height is plus 1. They are like a similar shape. So we will get same area, but one will be negative area, one will be positive area. So DC component of this signal is 0. Okay. So what about this signal? This is even or odd signal? Okay. So this question you can write. Last, just I will come back to this problem. Okay. Fine. So now what we came to know here is that signal can be even, signal can be odd, signal can have DC component. Yeah. If signal is neither even or not odd, so in that signal also we have a even part and odd part. Okay. So this is the simple formula to calculate even and odd part. Okay. If we take signal, if we time reverse that signal, if you add them and divide by 2, we will get the even part. If you subtract and divide by 2, you will get the odd part. Okay. Fine. So very simple signal I will take. So here just my motive is to show you that we can construct any signal by taking its DC component, by taking its even part and by taking its odd part. So if this is the signal, in order to calculate even part, what is the first step? First I have to flip this signal. Yeah. This is the first part. I have to flip this signal. Fine. Now I have to add them. Okay. Because this signal is very simple. One signal is at right hand side of the origin, one is a left hand side of the origin. So there is no overlap. Fine. Simply if I divide the amplitude, then I will get my even signal. Okay. If just subtracting from this minus this, so now magnitude will be minus. So this is my odd signal. Fine. If I add these two signal, which signal I will get? Suppose I add this even and odd part, which signal I will get? Original signal. So now just we know that if you take any signal, okay, if divide into even and odd part, by adding them just we can get our original signal. Okay. So let us see this synthesis equation. Okay, we call this equation as a synthesis equation. Why? Because we can reconstruct our f of. Okay. So here we have to see what is this cos. Cos is even function or odd function? Cos is even function. What is sine? Sine is odd function. What is this a naught? This area we are calculating, yeah, over a period, average area. So this is a DC component. So what we are doing in Fourier series, basically we are calculating DC component of signal, we are calculating even part of signal, we are calculating odd part of the signal, and this we are adding them so that we can reconstruct our signal. Fine? In doubt here? So this is the basic our Fourier series. Okay? You calculate odd part, you calculate even part, and then you calculate DC component. Okay, if we add them, then we will get our original signal. Okay, so here where we are converting this signal into frequency domain. So many students come up with that question. Okay, so let us take some few simple example, then we will understand. Okay, this signal is even signal or odd signal? Even signal. So if I have to calculate Fourier series of this signal, then I just need to calculate the even component. Okay, that means this harmonic of cos. Fine, harmonic of cos. DC component is also not there. Okay, if I have to calculate this signal, okay, then simply I can calculate the harmonic of sine. Fine, so I don't need to calculate any other component. Any doubt up to here? So one simulator is there. Okay, just we will simulate some problem, and just I will show you how we can reconstruct signal. Fine. So this is one square wave. Okay, basically what we are doing. Okay, you can see here. So if we take different harmonic of cos and sine, here this is even. So let us take or odd. Only one harmonic we are considering. DC part is 0. So you can see that how I got this square wave. They are just a sign of different harmonic, but they have different amplitude. Okay, you can see that when I am adding, if I add enough number of harmonic, then I will get my original signal. Okay, just we are just considering 6 harmonic only, 5 or 6 harmonic. So my that signal is not that smooth. Okay, here what we are doing, that we are calculating suppose this one. Okay, so 2 pi f n t. Fine. So at first fundamental frequency f naught. Okay, if it is the fundamental frequency, then what will happen here, you see. Okay, basically what we are doing is that just I am taking this signal. Fine, for our simplicity I am just considering one time period. Now I am multiplying with cos with same frequency of this signal, so overlap will be higher. So you can see that every time my A1 is always higher than other component. Fine. So this area we are calculating. The value of this A1 is nothing but the overlap between my cos and my given signal. Okay. Let us increase. If you suppose further increase, now we have like this. Okay. What will be the overlapping area in this case? Okay. Let us take this one only. Okay. What will be the overlapping in this case? This part is overlapping. This part is overlapping. What is total overlapping area? 0. Fine. So maybe we will get A to 0. Then again we change our harmonic, second harmonic. Suppose I am doing like this. Then suppose let us consider like this. Okay, for our simplicity I will consider this and this. Fine. So this part is 0 and only overlapping part is this component. Okay, so that area which is overlapping with this my whenever I am taking n is equal to 3, okay, 3 into f naught. So this much area is overlapping. Okay, remaining area is the positive, negative, it will cancel out. So we will get some value of A3. Fine. So what we are doing, we are taking different harmonic and we are seeing that how much it is similar to my signal. We are just overlapping them, and then we are calculating area, overlapping area. That overlapping area gives us the similarity. Okay, suppose if I give you 2 pictures, how do you recognize this is mine picture or his picture? You just superimpose that image on my face and his face. Okay, that our mind is doing that. No? How this convolution, see, and then how it works. It will take signal and that it convolve. Okay, that is just a convolving and finding that similarity. Okay, how much similarity is there? So obviously, whenever we take first f naught, so more similarity will be there because both have a same frequency. As we increase the frequency, the negative and positive part tend to cut, and the overlap will be smaller and smaller. So as we increase towards n, so that overlap will be lesser and lesser. Okay, fine. So because here if I give you suppose one simple signal, okay, okay, I have one example, I will show you that. So first harmonic, so area overlapping is more, not first harmonic, fundamental frequency overlapping is more, so A0 will get more. So if I take another frequency, then maybe we will have a less overlap, but if we add them, then we will get some signal. If we keep increasing, then we can reconstruct our original signal. But like how many that n we take, this we cannot avoid. Okay, do you know what is this phenomena is called? As I have undershooting and overshooting. Gibbs phenomena or Gibbs phenomena will have. Okay, what is the frequency of this signal? 3 time it is around 3 time peak 3 is there in 1 second. So in 1 second it is repeating 3 time. What will be the frequency? 3. In 1 second it is repeating around 5 time. What will be the frequency? Hertz means like how many time it repeats itself in 1 second. That is 1 hertz. Yeah. So peak if you see, then if I take a Fourier series of this particular signal, okay, so what kind of graph I will get if I plot this into frequency domain? What kind of graph I will get? How many frequency component are there? How many? 1. Fine, only one frequency component. If I multiply that with same suppose fundamental frequency, then overlapping is maximum, that area I will get. If I take any other frequency, then you will see that the plus minus will cancel each other and all the harmonics will be 0. Okay, why it will be 0? Because of this. Okay, so positive half cycle, negative half cycle, and resultant area is 0. So if I plot this into frequency domain, okay, so suppose this axis is my frequency domain axis. Okay, suppose let us say 1, 2, 3, 4, and suppose amplitude is A1, suppose. Fine. So what kind of graph I will get? How many frequency component are there? 1. What is the amplitude of that? A0. Let us, so A0 is here. So frequency of this one is 3. So here it is 0, no DC component. 1 hertz is not there, 2 hertz is not there. We will just get simple line at 3. Only one harmonic is, only one frequency component is there. All harmonic are 0. Okay, so just we will get one straight line when my f is equal to 3, when my f is equal to fundamental frequency. Okay, this is how it looks in frequency domain. Okay, so you can see here. Similarly, if I draw for this one, which frequency component is present here? 5. So I will get one component over here in 5. Obviously, amplitude is more this one. So I will get somewhere. Sorry, this is, let us consider 5. So I will get one spike at 5. Okay, if we take, because sine and cos are easier, na? By observing sine and cos, we can easily determine which frequency it has. Yeah. So if sine and cos is there, so we don't need to calculate the Fourier series also. Directly we can see how many times they are repeating in 1 second, then we will get to know that, okay, that is the frequency component of my signal. Okay, fine. Now this signal is there now. What I did, just I added these two signal and I got new signal. Okay, here signal was very clear. Okay, so it was very easy, just we calculated how many peaks are there. Okay, 3 peaks, we tell, okay, 3, 5 peaks, we said that 5. But here though it is a bit random, no? So it is very difficult to see, okay, which frequency component are there. But if I take Fourier series of this signal, but we know that, na? I have added this signal and got this signal. So how many frequency component are there in this signal? 2. One is 3, one is 5. So if I take the Fourier series, then I will get these 2 frequency component. Okay, we know that. Okay. Now suppose now I am adding some noise. Okay, can we tell that what is the frequency component here? What is the frequency component here? Okay, but if I convert it into frequency domain, okay, then this harmonic, so I will get something like that. Okay, so here you can see that now all other noises have like a very little contribution. Main signal is at 3 hertz, main signal is at 5 hertz. Okay, so you can see that now by converting, by here time domain, though we are just unable to extract any information. Yeah, but it's soon as I converted that signal into frequency domain, now we can make some sense of this signal. Okay, if I have to filter, now I can put some filter of low pass filter or band pass filter, which will just pass 3 here, around 5, and similarly I can make nose filter here, then I can get my output. Okay, so this is also one of the advantage of converting frequency from signal from time to frequency. What we did in Fourier series, just we took different harmonic, we calculated what is area overlapping between our given signal and those harmonic. That is nothing but my A1, A2, A3. When I multiplied A0, A1 with my fundamental frequency, A2 with my first harmonic, A3 with my second harmonic, when I added them, we got our original signal. Okay, fine. Any doubt here in Fourier series? So Fourier transform, or we should conclude here. Fourier transform also you want to see? Fourier series, so we know that if signal is periodic, then we can do the Fourier series. If signal is aperiodic, then Fourier series we cannot do. In that case, we will go for Fourier transform. This formula, and all of are aware of this one. So just I will show you. If I take this rectangular signal, then what will be the Fourier transform of this signal? Very standard. Yeah, all communications we keep on doing. If it is rectangular, then it is sync. Okay, look here. Fourier transform and Fourier series are almost identical. The idea is take one frequency, multiply with our signal, and check the overlap. Whichever frequency component has more overlap, we will say that is the dominating frequency. Okay, same idea. Only difference is that periodic signal was there, so fundamental period of signal was known to us. So we exploited that in Fourier series. So we said that, okay, why I should check all frequency from minus infinite to infinite. I know that fundamental frequency is f0, so f0 will have maximum overlap, its harmonic will have some overlap. So that case we have simplified our analysis. Okay, because some known thing is there, na? So I know this frequency, this signal has this much frequency, so we exploited that information, and accordingly we have simplified our calculation and got our result. But here a periodic signal, I don't know like which period this is the simple square wave, so it is easier to interpret. In real life though, many different kind of signal we will get, na? So it is very difficult to predict. So what we will do here, what we are doing is that instead of taking like discrete signal, we will take signal from like minus infinite to infinite. All frequency component we will take, we multiply, and we check for the overlap. And whatever overlap we will get, we keep on integrating them. So because we know that our system is linear, so Fourier series and Fourier transform is linear. So I can take one signal, multiply that one, and keep that result. Second signal, multiply, keep that result. Third signal, multiply, keep that result. If I add them all together, I will get the final result. Yeah. So that linearity is there, additivity is there, homogeneity is there. So I can do that. This is the formula. Fine. Any signal will have a AC the odd and even component. So here this is Euler theorem. Yeah. So this has how many components? This has cos and sine. Two components are there. So if I am multiplying with complex exponential, that means I am multiplying my signal with cos and sine. Okay, that's what I am doing. So you can see that this is our two component. Now we will multiply this. Now we can separate them for our visualization. Okay, cos will give us a real part, sine will give us an imaginary part. Okay, and then we can get some phase and we can get some amplitude. If we keep on doing, then we will get something like this. Okay, fine. So this we are aware of this one. So this is what we are doing in Fourier transform basically. If you see interpretation. So I have one sine component, I have one cos component. Okay. First I will take some frequency. Okay. Let us take some frequency omega 3 or something. Okay. Okay. Let us calculate it 0. What will be the amplitude of my signal is 0 in frequency? Sine 0, cos 0. So whatever area is there, I will get same area. So 0 I will get 1 because the area of this is 1. Okay, let us take some omega is equal to 3. So you can see that overlap in cos is there. So this is my area I will get. Overlap here is resultant is 0. So I don't get any imaginary component. I will just get some real number. So that real number is 0.666 if you measure, sorry, gone. Fine, I will show you here. 3. So this is my overlap. So that area of sine is gone. Area of cos, I will get something. At omega is equal to 3, we will get this area. Okay. Similarly, if you take some other value of omega, what we are doing basically, we are taking sine and cos and we are multiplying with this signal and finding the area under those overlapping area. Okay, and then we are calculating that. Okay, fine. If you see here 0, so I have already given this example. Sine 0 will be 0, cos 0 will be 1. So we don't have any imaginary component over here, only real component we will get. So that's why at 0 frequency the amplitude of my sink is 1. Okay, if you calculate in between here, here, you will get 0. Okay, got the point? What we are doing in Fourier transform, taking signal, okay, one sinusoidal signal, even an odd part, now we are changing the frequency and multiplying and checking the how much similarity is there. Okay, accordingly, whenever we have more similarity, we will say that that is the dominant frequency component of my signal. Okay, fine. Fourier series and Fourier transform are same method. Only difference is that Fourier series, I know the fundamental frequency, so I don't need to just look for all frequency from minus infinite to infinite. I can start from my fundamental frequency and I can take the harmonic. Here it is aperiodic, so that benefit is not over there. Now I have to check for all the frequency component minus infinite to infinite. But basically we are doing same. One is in discrete, so it is easy to visualize. Here same thing is happening continuous. So omega is 0, 0.0001, okay, then 0.0002, something like that. Okay. Same thing here. So that if you take omega is equal to 22 or something like that, so you can see how much overlap is there. That area we can calculate. That is the area we got here. Okay, fine. So if you see, then if just here for our sake, I have just some frequency. You can see multiplying and calculating area under that frequency, and if we sum all of them, we will get the sync signal. Okay. So fine, in doubt? Okay, thank you.